Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at trigonometric graphs. So let's start out by looking at the graph of y equals cos x. So hopefully by now you know that cos x lives between -1 and 1. So how we graph this, we can get our information from the unit circle. We know cos of 0 is 1, cos of 90 degrees or pi on 2 radians is 0, cos of 180 is -1, then cos of 270 is 0, and cos of 360 is 1. So we just join this up in a smooth curve. This is the graph of y equals cos x. Now it keeps going up and down like that forever and ever. Both directions. So this is the graph of y equals cos x. What about the graph of y equals sine x? So we know that sine of 0 is 0, sine of 90 or pi on 2 is 1, then it goes back to 0, down to -1, and sine of 360 is 0. So the graph of y equals sine x looks like this. Again, it keeps going forever in both directions. So it turns out that sine and cos are what we call phase shifts of each other. If you move the blue graph, cos, over by 90 degrees, you get the sine graph. If you move the sine graph to the left by 90 degrees, you get the cosine graph. So let's look at some features of this graph. So both of these graphs have a midline. They have something that goes right through the center of the graph, and that's the x-axis here. Of course, the x-axis has equation y equals 0. So the amplitude of the graph is the distance from the midline here to the peak. So the distance vertically is 1. It only ever goes 1 up from the midline, that's as high as it goes, and as low as it goes is 1 down from the midline. So because it goes between 1 up and 1 down, we say the amplitude is 1. So the first peak, so peak is when it equals, in this case, 1. You can see for cos, the first peak occurs at x equals 0. That's the first peak that is on or after the y-axis. And you can see the first peak for sine occurs when x is equal to 90 degrees or pi on 2 radians. So the period of both graphs, which means the distance between peaks, is also the same. So the distance, the horizontal distance between the peaks is 360 degrees or 2 pi radians. That's true for cos. It's also true for sine. Sine actually has another peak over here at 450 degrees. So we say that the period is 360 degrees. Now I just want to make the point that it does sort of matter whether you're graphing in degrees or radians. So for y equals cos x and y equals sine x, if you graph in radians instead of degrees, the graphs will look the same. The only difference is the scale along this x-axis. We would use the red scale if we were graphing in radians and the black scale if we were graphing in degrees. So you can see that for these two graphs, they have pretty much the same features, same period, same amplitude, and same midline. The only difference is where the peak occurs. The only difference is a horizontal shift. Everything else is the same between these two. But of course, we want to be able to graph different types of sine and cosine functions. So let's look at that now. So we want to be able to graph equations of the form y equals a times sine or cos of b outside of x plus c plus d. So when you're graphing an equation of that form, it's always going to have the same up and down wavy feature that you just saw in the sine and cosine graphs. But the features we went through, the midline, amplitude, peak, and period, and so on, they will change. So what you do when you have to graph an equation of this form is identify these features. So the first thing that you do, I want you to do in this order, go D, A, C, B. First thing you identify is the midline. So let's look at the graph of y equals 2 sine of this plus 1. This number d out the end, that is the midline. So what I'm going to do is I'm going to draw the midline here at y equals +1. So this will be the midline of the graph. Next, we look at the amplitude. The amplitude is whatever a is. So in this equation here, the amplitude is 2. So remember that the amplitude is the distance from the midline up and down. So the midline's 1, The highest value, the peak of this graph, will occur at 1 plus 2, 2 up from the midline. So here at 3, this is where the graph will reach a peak. And then the lowest value that this graph will take is 1 minus 2, 2 down from the midline, which is down here. That's what's called the nadir of the graph. So this graph that I showed up here, it will live between this line and this line. It'll go up and down, up and down, up and down. But we still need a bit more information. We need to know where the peaks are. So after we've done D and A, we're going to identify the first peak. So the first peak occurs at 0 for cos, and for sine it occurs at 90 degrees or pi on 2 radians. What we're going to do is find where the first peak of this graph occurs. So since the peak of a sine graph occurs when its argument, the thing you're putting inside the sine function, equals, in this case, pi on 2, we're going to solve the equation 2 outside of x minus pi on 2 is equal to pi on 2. Because if this whole bracket equals pi on 2, you are at a maximum. Sine pi on 2 is the maximum. So to solve this equation, we're going to start by dividing each side by 2. And then we need to add pi on 2 to both sides. So pi on 4 plus pi on 2 is equal to 3 pi on 4. So 3 pi on 4 actually occurs here, halfway between pi on 2 and pi. So the peak is going to occur here. That's just a peak of the graph. Now we're going to identify the period. So the period, if you're in degrees, is 360 over b and radians 2 pi over b. Our b value here is 2. What that means is the period is going to be 2 pi over 2, which of course equals pi. The period is the distance between peaks. So we had a peak here at 3 pi on 4. There will be another peak in pi. 3 pi on 4 plus pi is 7 pi on 4, which is over here. It also means it'll have a peak pi over this way. So this was 3 pi on 4. It will actually have another peak over here at negative pi on 4, which is about there. Now, of course, note that the nadirs, the low points of the graph, they always occur halfway between the peaks. So you can see here we've gone 1, 2, 3, 4 divisions across. So the low point will occur down here. Similarly, there will be a low point down here. So this is pretty much all we need to be able to graph this function. We know that it hits its peak, it's going to come down, stop, turn around, and it's just going to keep going like this in a wave-like motion. And we've now done it. We have drawn the graph here. And we see how easy it is when we first identify its features. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.